everyone. Welcome to my YouTube channel, The Learning Hub. In today's video, we are going to discuss about context-free grammar and context-free languages. So, before beginning, let us first understand what is there in regular grammar and what is there in context-free grammar. So, we know that in when we talk of regular grammar, the regular grammar is used to design regular language, and from this regular language is run on finite automata machines. And from this, similarly, we have context free grammar. Using context free grammar, we design context free languages, and the context free languages run on PDA, that is push down automata, that we will be discussing in detail about in the next few videos. So context free languages basically are applied in parser design. So these are used in parser designs, like the compiler has a parser, so it is used over there. They are useful for describing uh, block structures of programming languages. So here we say the role of context free languages is to is to be useful in parsing, and they are where we can describe the block structures of programming languages. So let's understand the definition of context-free grammar. So before understanding the definition of context-free grammar, let's understand what was there in regular grammar. Now suppose when we are talking of any language, regular language, in which we have a language like a raised to power n and b raised to power n. What does it mean over here? So a raised to power n in b raised to power n, we are generating a string. If we say we are talking about infinite values, infinite, that is n starting from 1 to up to n, and we are not having any infinite value in that case, and we want to generate this language using finite automata, it is not at all possible, because finite automata has limits. Suppose the value of n is equal to 2 a raised to power 2 b raised to power 2, that is 2 times a and 2 times b, or a raised to power 5 or b raised to power 5. This can be designed using uh, finite automata, because here we can specify for the value of this 5 we will be having minimum 5 states. So we have finite number of states, as finite automata names is self-descriptory. Finite automata, that is finite number of states, and this finite number of states is here to describe the regular language. And it can if we design a minimum automata, this finite automata, then it can be for this state q naught with this and this can be the minimum automata, but it cannot describe how many occurrences of a and b can be there. So for simplicity, we can simply say finite automata cannot be designed for infinite states. So we call those infinite state as the terminology of saying context free. And for such cases, for infinite states, infinite stages, we have context free grammars. So the definition of context free grammar says, suppose we are having a language G, which is a context free grammar, if in every production which is having of the form a raised to power alpha, where this a belongs to set of vertices n, and this alpha which we are talking of is those set of vertices, and we apply certain alphabet and we get the infinite states. So these vertices having few states, we apply certain input value alphabets, and this can be go into infinite. So here we say about this definition, we say G is equal to V sigma S and P, where this V is nothing else, this is basically set of variables, or we can call them non-terminals also, variables or non-terminals. And this sigma is just like any other language, which is set of terminals. or we call them alphabets or string that is being generated. And then we have this s is nothing else. This is just similar to like we are having q naught, and that is the initial state in regular expressions, and here we are having s, which is a start symbol. So here we are not designing any type of state machines, we are designing with a start machine. And then this p is basically a production rule. Production rule plays very important role in finite automata because it gives the basic rule of generating the finite automata machines. So the difference of context free grammar and the regular grammar is simply that context free grammar has a production rule which is of the form a raised to power alpha, where alpha is variables union any signal applied, and this basically a belongs to any of the variable. So now we will be discussing a few examples of this context free grammars, how we can design context free grammar and language. Okay, so let's discuss few examples of context free grammar. Now suppose the question comes, create a or construct a context free grammar for a language, context free grammar for a language having number of a's over the set this is equal to a. So here it says any number of a's, that is a raised to power n. So here we know that sigma is equal to a, that is symbol. Now the language will be something like, because here it is saying any number of a's, it means it is there is a possibility that there is no a. So that is string with length 0, which is represented with epsilon, and then 1a, 2a, 3a's, and so on. So this is the possible language. Now but can be the production rule? For that we have to design a production rule in this case. So the production rule is something like this, which says s is starting symbol, this is mandatory rule, a followed by s, which again can go as first production rule, and we can also say what is s, a. So what is happening over here, if we start with this, we are saying as, this a is further substituted as a. If we want to generate two a's, and if for anything if we want to generate two 3a's, then we will go like this, as we will substitute the starting value as, we have to start from here, then as, then this as can be further expanded as per requirement. So this is how we can generate this particular language for any number of a's using this production rule. So now let's construct a context free grammar which is some like w c w r. What is over here? It is saying where w belongs to a comma b star. So here a b star represents this belongs to w, value of w, which is w is a string over here, and wr is basically reverse string. Now w consists of ab. Suppose the string is ab, then wr will be ba. So the complete language will become ab ba. Now suppose it consists of w consists of aab, then wr will consist of b a, that is reverse of this, and the combined string will become a b b a. So this is the complete string. So this language is something like this, a c a, because c is a constant that is being written in this case. Now a c a. Now this is the w, this is the reverse of w, and this is the constant which is inside this. It can be bcb, it can be bb cbb. Fine. It can also be a string like this. It can be A, B, C, B, or anything which can be written like this. So now we will have to design production rule for this, that is the value of P. So the minimum production rule is, suppose A, we are talking about this initially, so we can write it A as A. Let us consider this. There can be BCB also, because this is the minimum rule, so we will write as B S B. Let us consider it as the second one. And now what should be the value of S in this case? It should be C. Now let's test whether this production rule is satisfying all the required conditions or not. So let's check for ACA. So how will we work in that case? For ACA, we will say S, we will apply first rule, that is ASA. So now we will substitute the value of SSC, we will get ACA. Now suppose we want to generate BCB, that is this value. So we will proceed with the second rule. Now rule number 2, that is BSB. So we substitute SSC, we will get BCB. Now similarly, suppose we want to get the rule of ABCBA. We want to generate this string of the language. Then how we can go with this? We will simply put the values like S, because we have to start with A and end with A. So we will apply the rule number 1, that is ASA. Now what is next we require? We require B in this case. So we will put the rule number 2. So that is apply rule 2. We will get B A. For the value of S, we substitute BCB. So we put B C B A. Fine. So basically this is S in this case. Now from this we have got AB. We want to get ACA. So what we need to put? We will put A B, and we substitute rule number 3 as C, that is A B C B A. So this is how we can generate the number of substitution we apply, and we get the desired string. So we say this production rule is sufficient, and we will get the grammar for this case. Now let's suppose we want to create a grammar that says any number of A's and B's. So what is this? Here we are talking of A plus B. The language is like L belongs to this, because any number AB, AA, it can be BB, it can be BAB, it can be BA, or likewise. So here let's generate what can be the production rule values for P. It will be either AS or BS or epsilon in this case. So we go with the language S, comma A, comma B, comma P, comma S. So this is how we proceed. Now let's discuss another example that says the context-free grammar. Context-free grammar which consists of at least 2 A's. Fine. So when we talk of at least 2 A's, what does it mean? The regular expression here should be something like let's have a look at this example, which says now we have context free grammar of at least 2 A's. So when we want at least 2 A's, then it means the grammar is of something like this: AA. These are the 2 positions that are to be phrased. It can begin with B, they can have in between B, it can end with B, it can be AA also. So it can be anything, but the thing is we have to phrase it with 2 values. They can be the starting values or they can end with any value. So to make such a string which consists of a language like minimum 2 A's should be there. It can be ABA, here 2 A's, BA, BA, B triple A. So all are possible. So when we have to talk about this type of grammar, then we can say there can be a regular expression which is of the form which says it should be followed. There should be at least 2 A's. We know it can begin with any other letter, so we will write A plus B star, means it can begin with anyone, and then there should one A should be there. Also there can be anything in between these two. If we look at this also, if we look at this also, so this is following satisfying the criteria. Also it can end with any value, either A or B or any number of A or B's. So this type of regular expression is possible in such case. Now what type of production rule can be there? It is very simple. It can be freeze the two values that we require. Now the other is A plus B star. It can be anything. So we can say, let us take another variable which says for this cases A plus B star, A plus B star, A plus B star. We will take another variable. Now what should be there in this variable? We can have A followed by anything, B followed by any such string, and epsilon, because it can have 2 A's only. So we, in that case, this A should be epsilon, which is epsilon A, epsilon A, epsilon is equal to AA. So this is how this grammar can be written and what is the production rule for such case. Now similarly, if we have a grammar that says at least one occurrence of 000, again very simple, so we can say 000, there should be occurrence, means all these three should appear together, but in front of it or at the end of it, anything is possible. So what can be this A? This A can be either 0, 0, it can be 1, 1, 1, 0, anything, it can be epsilon also. So this is the production rule for the case. Now let us consider the case which says A raised to power n, B raised to power n, where n is greater than equal to 1. So for such case, the language will be AB, AA, BB, AAA, BBB, because this is the case equal number of A's and equal number of B's. So here it will be something like this: A, S, B, means A or B. This, what can be this S? This can be repeated, and it can be this AB. So this is the production rule. When we substitute the value in this case like A, S, B, it can be substituted as AB, which will become AA, BB. Also suppose we want this value, so what will we do? We will substitute A, S, B. For this S we will again substitute A, S, B, and for this S we will substitute AB. Now reading this value we will get AAA, BB, B. So this is the possible grammar for such case. So these all are about examples of context-free grammar. In the next video we will be discussing about derivation trees and yield offer tree. So thanks for watching the video.